Hey everybody, we're going to look at finding maximums and minimums of functions of several variables. And this is something that, a big takeaway from Calc 1 is that we find derivatives in order to find maximums and minimums. Well, you'll see that this is very similar in some ways. But there's going to be, it's going to be a little bit more complicated because we have two variables, or potentially three variables. The idea extends, but we're really going to be looking at just the two variable case in this course. Okay, so just to define, we're talking about local minimum first. The function f of xy has a local minimum at ab if f of ab is less than or equal to f of xy, as long as xy is near ab. When we say near, it means as long as we could find some open circle, an open disk with an epsilon radius, and that's true for all points within that open disk, open circle. And just to be clear, we call f of ab the local minimum. All right, the local minimum is the value of the function. It has a local minimum at the point AB. And we'll flip the inequality around to define a local maximum. So the function's local maximum has a local maximum at AB if f of AB is greater than or equal to f of xy for any xy that's in some epsilon disk near AB. Okay, so the inequalities, I guess we should point out then if this inequality should hold for all xy, like in the entire domain, then we would call this an absolute maximum or minimum rather than a local. And sometimes we say global instead of absolute. You're familiar with this language, probably. Okay, so a main theorem that's going to allow us to, or it's going to help us to find local maximums and minimums if the function has a local maximum or minimum at a point AB, and if the first order partial derivatives exist, then it must be the case that the partial derivative with respect to x and with respect to y at this point must be 0. Now, it doesn't necessarily mean that as long as f of x, as long as the partial derivative is equal to 0, it doesn't necessarily mean that you have a local max or min. It could be something else, but we do say if the first partial derivatives both equal 0 at AB, or if either of these partial derivatives don't exist at that point, we call AB a critical point, just as we do with one variable calculus. And so we're going to go through and find critical points, and then we're going to determine whether they're maximums and minimums and so forth, and we'll see how we do that. Okay, we have this function f of xy, x squared plus y squared minus 2x minus 6y. If we want to find the critical points, we have to find the partial derivatives, right? So it's going to be 2x minus 2, and the partial derivative with respect to y is going to be 2y minus 6, and so we just set 2x minus 2 equal to 0. That means x equals 1, and 2y equal to 6 means that y is going to be 3. Then we have the point 1 comma 3 is the only critical point, right? Because the partial derivatives exist for all values of x and y. It's only for this particular pair of xy that you get 0 for both partial derivatives. So here's another example. F of xy equals y squared minus x squared. So if we wanted to find the partial derivatives here, we're going to have minus 2x. Fy is going to be it's going to be positive 2y, and so the partial derivatives, if you set them equal to 0, x equals 0, and 0 equals 2y, that means that y has to be equal to 0. So the only point 0, 0 is the only critical point, but we could observe, for example, that f of, say, 1, 0 is greater than f of 0, 0, right? If you plug in 1 for, oh, I'm sorry. I meant to put that in for y. Let me say, if f of 0, 1 is greater than f of 0, 0, right? Because you would have 1 squared minus 0. That's 1 greater than 0. And, but that's greater than f of that's greater than f of 1, 0, which is going to be negative 1, right? So what we have is a critical point, but it is not a local maximum. It's not a maximum or a minimum. In fact, you can't find any circle around this where you're going to have where 0 is the maximum. So if you can see any little epsilon away in the x direction, you'll have a function value less than 0. Any epsilon distance away in the y direction, you'll have a function value that's greater than. So so yeah, this is not a critical point, but this is what you call a saddle point. And this is kind of these saddle points are found on Pringles, these hyperbolic paraboloids, for example, but they can be found in other surfaces, other functions. Okay, so we'll go through the second derivative test. Now, this is a way that we test functions of two variables, test a critical point to see whether it's a maximum or a minimum or neither. And so we're going to use this this value d, which is going to be the second partial derivative with respect to x, like fxx, times fyy at ab minus fxy ab squared. Now you could actually do fxy times fyx, but remember Clairaut's theorem says that those mixed partial derivatives, those second partial mixed derivatives, are going to be equal to each other. So you have to calculate this d. Now we have, the test has really three possibilities. One, if d is greater than 0 and fxx, so the second partial derivative with respect to x at ab, is positive, then ab is a local minimum. And fxx is negative, right? If the second partial derivative, then f of ab is a local maximum. And then thirdly, if d is less than 0, then f of ab, I think I've been a little bit unclear about the notation. So here's the second derivative test. If d is positive and the second partial derivative with respect to x is positive also, then ab is a local minimum. If d is positive and the second partial derivative is negative, then ab is a local maximum. And then if d is negative, then we have a saddle point. So here's how you test these critical points. And in fact, you could even kind of modify this to, you could be testing the second partial derivative with respect to y to see if it's positive or negative. You'll have the same results. The idea being that, like, if the mixed partial derivatives are, so if fxx and fyy, if those are both, if they're the same sign, then you're going to be seeing this as a local minimum or maximum typically. But if I shouldn't say that that's not always the case, but certainly you can look at this and say, oh, if the second partial derivatives fxx and fyy, if those signs differ, then definitely you have a saddle point, right? Because that would definitely result in the first term being negative. And of course, the second term, you're subtracting something squared, so that's minus. So if the signs of the second partial derivatives differ, then you definitely are going to have a saddle point. So let's consider this function. F of xy is x to the fourth plus y to the fourth minus 4xy plus 1. So we're going to first try to find the critical points, right? So we have 4x to the third minus 4y. And then I'll take a step back and I'll do fy, the second partial, the partial derivative with respect to y. We have 4y to the third minus 4x. So if we set them equal to 0, what we get is 0 equals 4 times x to the third minus y, which means y equals x to the third. But over here, you can see similarly, you're going to get x equals y to the third. Well, the only way that this is going to possibly be the case, and you can see this by substitution, substitute this in for x, you get y equals y to the ninth. Or y to the ninth minus y equals 0. That means y times y to the eighth minus 1 equals 0. Well, okay, so either y is equal to 0 or y would be equal to 1 or y is equal to negative 1, right? Because you can see this, that actually factors into y to the fourth plus 1 times y to the fourth minus 1. We're not going to be dealing with any complex numbers, but there could be complex roots to this, of course. So anyway, we have three possibilities, and each of these you can see what x would be. X is going to be, let's see, to the third is going to be 0, x is equal to 1, or x equals to negative 1. Okay, so these are the critical points. Now we need to test these critical points. So we need to get these second partial derivatives. And so fxx is actually just going to be 12x. fyy is going to be 12y. And fxy is going to be negative 4. So you can see if we were testing d for each of these, I'll actually make a little table. I think that we can fit this thing in. So d, for the first one, remember d is the second partial with respect to x times the second partial with respect to y minus the second partial, the mixed partial squared. So that would end up, since at 0, 0, it's going to be 0 minus 16. At 1, 1, it's going to be 144 minus 16. And this is going to be also 144 minus 16. And here we can say, let's take a look at fxx. Only when this is positive do we care. When the d is positive, then we have to test the second partial with respect to x. You can see it's greater than 0 here, but it's less than 0 here. Just plugging in 1 or negative 1 in. So this is a saddle point. You have local minimums because you have 12x squared and 12y squared. So it doesn't matter whether x and y are negative or positive. This is going to be fxx is always positive, right? So yeah, we have local minimums for these two critical points, and we have this this other saddle point, and this is what they look like. You can see at these points, this is at the point 1, 1, and this is the point negative 1, negative 1. These are minimums, and what's happening here, if you look, you see that in one direction you've got this as a maximum, but in another direction you've got this as a minimum. So this is not going to be a local max or minimum, it's a saddle point. Okay, so let's say we're going to build a rectangular box with no lid, and we have 12 square meters of cardboard material to use. And we want to find out what's the maximum possible volume with that amount of surface area. Okay, so you've got, as a diagram, you want to have this in mind, right, where we have let's say we have let's say x, y, and let's put z as the height. Okay, so with no restrictions yet, but what we do have is that the surface area has to add up to 12 meters squared. So the surface area is going to be xy plus 2 times the sides that are xz plus 2 times the sides that are yz. So that's equal to 12. In fact, we can solve this for z and eliminate the variable z. What we're going to have, 12 minus xy equals, let's see, we can factor out the z and we get 2x plus 2y. So z is 12 minus xy over 2x plus 2y. So what is the volume of this thing? The volume is just x times y times z, but z is actually this other expression, which I'm going to write 12 minus xy over 2x plus 2y. And I'm going to just go ahead and distribute that. This is 12xy minus x squared y squared all over 2x plus 2y. So we have the volume of this thing. We want to now find the maximum possible volume. So we're going to take the derivatives and we're going to find the critical points, and then we're going to solve. We're going to test. Okay. So the partial derivative with respect to x, we're going to use the quotient rule. So we've got, it's going to be 12y minus 2xy squared, right, times the 2x plus 2y minus the 12xy minus x squared y squared times the derivative of this other expression, which is 2, and this is all over 2x plus 2y squared. And the nice thing is I don't need to actually, I don't have to do anything with this for the y, because I know that we're going to have symmetry. However, let's just take a look at simplifying this a bit if we can. Sure. So I'm gonna multiply this stuff out a little bit. So we're going to get up top, we're going to have a 12. I'm going to distribute, so we have 12y times 2x, so that's 12, that's 24 xy. And then we're going to have, let's see, plus 24y squared. Then we've got 12y minus 4x squared y squared, and then we've got minus 4xy to the third. And then we're going to minus this other stuff, which is going to be, well, it's a minus 24xy, and then a plus 2x squared y squared. So we do have a few things that at least cancel. So this and that, and then we have minus 4xy squared, and then we have the plus 2. So in the end, we're going to have, we'll have minus 2x squared y squared plus, let's do the xy term. So minus 4xy to the third plus 24y squared, all over 2x plus 2y squared. Okay, so we're going to, we have to solve this for, we're going to factor out actually a y squared. Let's do this on a new page. Okay, so I'm actually going to simplify this a little bit by factoring out from the numerator this common factor of this negative, well, actually not a negative, I'll just factor out the y squared, 2y squared. if I factor out 2y squared, what we're going to get from the numerator, we're going to have the negative x squared, we'll have minus 2xy, and then we'll have plus a 12. And then that's all over 2x plus 2y squared. Remember, well, by symmetry of this function, Vy is going to be 2x squared times negative y squared plus, minus 2xy plus 12 also over 2x plus 2y squared. We don't have to go through the whole rigmarole of taking the derivative with respect to y because the function is symmetric. So we can just swap the variables x and y, and we'll get that. Now, we know that the Vx equals 0 and Vy equals 0 will be solved when x equals y equals 0, but that's nonsense because we're looking to maximize the volume of this box, and you can't have one of the dimensions be 0. So instead, we can set the other things equal to each other. So minus x squared minus 2xy plus 12, set that equal to 0, and also set negative y squared minus 2xy plus 12 equal to 0. Of course, if those are equal to each other, then we can actually subtract one from the other. What we're going to get is well, that would be y squared minus x squared equals 0, which means that x minus y times, well, what does it mean? It means x equals y, right? That's the solution for that. Now, if x equals y, right? Because that's the only way that x squared or y squared minus x squared could possibly be equal to 0. But if that's the case, then we can just replace all the x's with y's in the equation. So we could write negative x squared minus 2x squared plus 12 equals 0, which is negative 3x squared plus 12 equals 0, which is going to be just x squared, x squared equals 4, right? That means x is going to be plus or minus 2. Well, if x is plus or minus 2, y is equal to x, so that means x equals y equals 2 would be the solutions for this thing. So those are the dimensions. So then what is the if going back to the original equation of the box, right? We'll see that if you take the equation for the surface area of the box equals 12 and plug in all these 2's, what we're going to have is 4 plus 4z plus 4z equals 12. That's going to be 8z equals 8, so z is equal to 1. So then a box that's of dimensions 2 by 2 by 1, that's going to be a box with a critical, what was it? It's either a maximum or a minimum or a value or a saddle point, I guess. This is going to be a critical point for volume, but of course, what does that mean? We can argue that this has to be the maximum value of the box, because certainly as if x, y, or z is able to go any higher, the other variables necessarily will have to shrink down. And so this volume is going to be increasing. Certainly, when any of the dimensions are 0, we're going to have a minimum value of the volume. It would be 0, right? And so certainly the maximum volume is going to be attained somewhere in the middle. And if this is the only critical point, it has to be a maximum. That's the only possibility. So this is going to be the dimensions of a box with maximum volume. Okay, so while some functions might increase infinitely or decrease infinitely in value on the entire R2, what we have is if you're looking only at a function on a closed bounded set, then you're guaranteed that you're going to have a maximum and a minimum, absolute maximum and minimum values of the function. This is just said in this theorem. If you have a function f, if it's continuous on some bounded set D in R, so like a rectangle or a circle or something, where the set includes the boundary points, then we're guaranteed that f will attain an absolute maximum value, f of x1, y1, and an absolute minimum value, f of x2, y2, at some points, x1, y1, and x2, y2, which it could happen at multiple points. there's one maximum value and one minimum value, right? That minimum value might be attained at multiple points, but there's one minimum value. That makes sense. You can't be less than the minimum value, otherwise that would be the minimum. All right. Okay, so let's consider this function f of xy, x squared minus 2xy plus 2y on this rectangle that's given. So we're looking at this rectangle that's going, let's see, 3 units in the x direction, 2 in the y direction. We want to find the absolute maximum and minimum values of the function on that rectangle. So first off, we're going to look for critical points. So this is going to be fx is going to be 2x minus 2y, and then fy is going to be minus 2x plus 2. Okay, so if you set these both equal to 0, what we're going to get is the first one gives you x equals y, and the second one's going to give you x equals 1, right? And so the only point that's a critical point would be the point 1, 1. Now, that's not the whole story. What we need to also look at is other possibilities. We have to look at the borders. We have to look at the borders, and we have to look at the corners. So on the borders, we're going to look at let's look at f of 0y. That's going to be the first, the vertical border, and that's going to be just 2y. And so there's no critical points here, right? The partial derivative of that is just going to be 0. So actually, we can plug in each of these things, these functions. We can look at, when we look at f of, let's say 3y, we can look on the border, on this border over here, that we're going to have 9 minus, that's going to be what, 6y plus 2y. Again, there's no critical points here either. No critical points. Let's look on the bottom border where we have f of x comma 0. Well, that's going to be just x squared. And I guess the only critical point here is going to be when x equals 0. And then when we have f of x comma 2, we have x squared minus 4x plus 4. That's a little bit more interesting. Let's see, that the partial derivative of that, f prime of x comma 2, we can look at just f prime because it's just a function of one variable. 2x minus 4, so when x equals 2, we have a critical point, right? So so then the critical point, we have to check this point here, this corner. We have to check the point here up there as well, and for good measure, we actually have to check all of the corners as well. Anytime the two corners join, it could be that you have a critical point at one of the corners. So we have to test all of these points. And really what we end up doing now is just taking the points x, y, and we're going to just evaluating f of x, y for all of these points. The point 0, 0, the point 0, 2, the point 2, 2, the point 3, 2, and the point 3, 0. Oh, and don't forget our friend 1, 1. So we have to evaluate the function at all these points, see what we get. We're going to get 0 for the first point, 0, 0. When x is 0 and y is 2, that's just going to give you a 4. When you have a 2, 2, what we have 4 squared minus 8 plus 4. So 4 minus 8 plus 4, that's a 0. 3, 2, what we're going to have is, let's see, 3 squared, that's 9 minus 6 times 2 is 12, plus a 4. Okay, so what we have there is 1, all right. 3, 0, we're going to have 9 when x is 3 and y is 0. And now at 1, 1, we're going to have 1 minus let's see, minus 1, 2, minus 2, plus 2. So this is another 1. So what is the so from this we would say this this is the absolute minimum value of this function. It's the value 0, and the absolute maximum value. Yeah, the point was that the maximum value here is taking place here, and the minimum value, actually we had two minimum values. We had a minimum occurring at this point and at this point as well. So you have to consider the critical points of the boundaries as well. Consider them as functions of just one variable. You might have to rewrite the function so that it's like a function of one variable. Like for example, if you're going up a diagonal, something like that. We'll do some examples like those later on. Okay, well that's it. All right, bye.